So last time we were looking at the Lagrangian formulation of field theories for the first time, where we introduced, based on an analogy with classical mechanics, the Lagrangian density curly L, which is a function of the fields and their derivatives, meaning that we treat the fields and the derivatives of the fields as the fundamental variables. So the principle, the action principle, if you like, is that the variation of the action should be zero, which means the integral of the variation of the Lagrangian should be zero. So that gives us two types of terms. One is the derivative of the Lagrangian with respect to the field. That's this first term here. And then we have all of the derivatives of the fields. So we vary the Lagrangian, we take the derivative of the Lagrangian with respect to the derivatives of the fields. And then we get this type of term. Then what we do is we use the following identity. We take this total divergence term and we just use the chain rule. So we get the two terms that you see below. And by definition, d mu of delta is delta of d mu. That's the definition of this functional variation delta. And we remember that this whole thing is a total divergence, which means we can rewrite the second term, because the second term is now here. So we rewrite this second term as the total divergence minus this term, which we take to the left-hand side. And that gives us a rewriting of the variation in terms of these three terms. But since the third one is total divergence, that will be assumed to vanish at the boundary of space if we're just working in a fixed region of space-time, or if we're working on the full space-time at infinity. So that then implies that the first two terms have to cancel each other out, and we get this set of equations here. Or one for each field, I mean, in that sense, set of equations. So these are the Euler-Lagrange equations, or we also call them the equations of motion. And as I was alluding to, if the Lagrangian depends on if there's more than one field, and we'll see some examples of that later on, then we apply this equation for all of the fields that are present. And the example that we finished up with last time is this Lagrangian that I've written down here, which is the Lagrangian for the Klein-Gordon equation. So you can check that, well, it's an exercise to check that that gives you, if using that Lagrangian, the Euler-Lagrange equations are the Klein-Gordon equation. And we'll do some more examples as we go along. Since L itself has no free Lorentz labels, it is itself Lorentz invariant. And that means that E squared equals P squared plus M squared will always be obeyed by the classical particle solutions. And more generally, it means that such Lorentz invariant Lagrangians describe Lorentz invariant physics. So physics which is governed by the rules of special relativity. Okay, so now we're going to come on to symmetries and what's called Noether's theorem. So this the derivation that we just had shows that if you shift the Lagrangian by a total derivative, then you'll get the same equations of motion as the original Lagrangian. And in particular, if you start with a Lagrangian and make a transformation of the fields, and that shifts you by a total derivative, the equations of motion will be the same. If this total derivative term is 0, even though J mu may be non-zero, then we have a symmetry in the system, and we'll have a corresponding conserved quantity. So that's what I'm saying on this slide here. So let's look at that in slightly more detail. So imagine now we make an operation which changes the fields to from phi to phi prime, and let's assume that this is just a shift of phi by some parameter times a field variation. Then just comparing that with our previous discussion, we'll get this total derivative term plus the equations of motion, all proportional to this parameter alpha, in this way of setting things up. So if the total derivative term vanishes, then we have a symmetry. And for the reasons we explained before, there'll be it's a symmetry because there's a conserved quantity that's independent of time. So the spatial integral of the time component of this current J mu is a conserved charge. And that's Noether's theorem, that for every symmetry of the action, there's a corresponding conserved charge. Right, there's a corresponding current, which is divergence free, and a conserved charge. Was there a question?
Yes. Can you go to the page 61?
Mm-hmm.
Now, even if derivative of J mu with respect to the coordinate mu and summing over the thing that you write up. Okay, if it's not 0, we can subtract it from what we have in the top of the page where you
That is
you write
yes, that
delta.
true, and we'll see an example of that later.
So it is a symmetry.
If delta L is a total divergence, then that is already, that preserves the equations of motion. So by an appropriate shift, as you were saying, one can define then a current J mu, which is conserved.
Mm-hmm.
Okay, and we'll see how it works. There'll be a lot of examples later and a lot of exercises.
Thank you.
Okay, so let's look at complex scalar field now. Now, this system, I've just defined a Lagrangian here for a complex scalar field. This has a U1 symmetry. Just to be pedantic, it's a U1 symmetry because, for example, so the U1 symmetry acts by multiplying phi by a pure phase, e to the I alpha. And so phi star phi will transform to phi star times e to the minus I alpha times e to the I alpha phi, which is equal to phi star phi. And similarly, the derivative term is the same because alpha is independent of the coordinates. And you get the same invariance properties. So this is why this system has a symmetry under phase rotations. And so this is a U1 transformation. It's e to the I alpha is a general element of the group of 1 by 1 unitary matrices. And we can make contact with what we had before by, for example, expanding the field, the transformed field, for small values of alpha, as we're sort of used to anyway in thinking about Lie algebras. So in this case, we can compute the J mu. So if we look at, so this is the quantity which appears in our variation of the action. So if I take the action and I look at how it depends on d mu phi, the action depends on d mu phi through the first term. And the coefficient of the first term is d mu phi star. And since phi and phi star are independent variables, this is just remember that phi and phi star are independent variables. Now we have two fields as opposed to one in this system. So the coefficient of d mu phi is d mu phi star, and now we multiply by the variation of phi dividing by the parameter, and that gives me I times phi. Then since we have more than one field transforming under that symmetry, we have to take into account, we have to add the contribution from the other field, which transforms under the symmetry. And from that, we get the complex conjugate term. And if you add them together, then we get an expression for the current associated to this U1 symmetry. And that gives us this expression here, which is exactly the J mu that we had derived directly from the Klein-Gordon equation. So now we see that the reason that this conserved current is there is because the system has a symmetry. And the integral of the time component of this current will actually be the charge associated to this symmetry. Just to note that alpha goes from 0 to 2 pi. One can ask about different charges under U1 transformations. So under a U1 transformation, the charges must be integers. And the way we've defined the transformation of phi goes to e to the I alpha phi. That's what we call charge 1. But one can have any integer charge where q is an integer labeling that charge, and charge q would correspond to inserting an extra factor of q in front of alpha. And that would actually then put the charge in front of the current. Which is also the expression that we had in the end, because we wanted to eliminate or interpret the negative energy solutions of the Klein-Gordon equation in terms of antiparticles.
Sure. Is there any reason why the charge must be an integer? It's like it could be an arbitrary real numbers, right?
Well, a mathematician would tell you that the representations of U1 are given by integers. And that is true because it's related to quantization of fluxes. Let's say, for example, if you well, I mean, in order to really answer the question, one would have to couple this U1 to a background, couple this field to a background gauge field. We haven't introduced gauge fields yet. But if you do that, then the integral of an appropriate magnetic field strength over any closed two-dimensional surface in a suitable normalization has to be equal to an integer.
But for example, if I take the quarks as a field here, it also satisfies the U1 symmetry, and the charge of it is like a fraction. Yeah,
but you can redefine the charges of the standard model fields by multiplying by a third or a sixth. So electric charge is given by E, and E is just a number in natural units of order, roughly 1/3. But you have to take that normalization constant out in trying to define the globally defined charges. Okay. So it's okay for most applications in physics, because we don't, in particle physics, we don't often have to worry about the topology of the field space. But if you worry about the topology of the field space carefully, then the charges are integers.
Okay, thank you.
Okay, what I'm gonna do next, for the next, well, for a little while now, is we're gonna look at electromagnetism as a field theory and Maxwell's equations. And then we'll come back to symmetries again. So here, at the top here, I've written down Maxwell's equations. So the first equation tells us that the divergence, so remember that Maxwell's equations depend on an electric field and a magnetic field. So EI and BI, and they're both three-dimensional, they're both vector fields in space. So they have three components. So the first equation tells us that the divergence of the electric field is equal to the charge density, rho. The second equation tells us that the curl of the magnetic field minus the time derivative of the electric field is equal to the current, J. The third equation here is telling us that the magnetic field is divergence free. And then the last one tells us that the curl of the electric field plus the time derivative of the B field, the magnetic field, is 0. So here, just to be clear, if you want to compare this with previous studies or other texts, this is written in Heaviside units, in which I've also put C equals to 1. Charge conservation is expressed through this equation, like as which we can rewrite as a divergence equation, and some textbooks use H instead of B. Okay, so what we're going to do is reformulate Maxwell's equations as a Lorentz invariant system, or a Lorentz invariant field theory. Okay, so the first thing we do is we're going to introduce a 4x4 matrix whose indices are the Lorentz labels. So F mu nu is just a matrix whose entries are the electric and magnetic fields arranged in some way. I mean, just arranged in the way that I've defined here. You can check that F mu nu upper is the same as F mu nu lower, except that E goes to minus E. So you notice that as a matrix, as matrices, these are anti-symmetric, meaning if I swap mu and nu, I get a minus sign. And this F mu nu transforms as a tensor under the Lorentz group because it has these two Lorentz labels. And we say that it's a second rank anti-symmetric tensor field. And the usual name given to the F mu nu is the electromagnetic field strength, or electromagnetic field strength tensor. So if we write out the spatial components, or if we break down the components of F mu nu, we see that F0I lower is the electric field, and Fij is given by minus epsilon ijk bk. And here we see that this is, we can explain why F0J upper is minus the electric field. It's because we've had to raise one spatial index from lower to upper, and we're using the mostly minus convention for the metric. So we get a minus sign. Whereas for the magnetic field, Fij, we're raising two indices, so we get two signs and they cancel each other out. So we can actually then rewrite Maxwell's equations in terms of the field strength. And so we get that the divergence of F0I upper is minus the charge density. That's equation A. And that's the same as the, that's equivalent to the divergence equation for the electric field. This equation B is taking a divergence of the B field and also taking the time derivative of the electric field. So if we look back, that's this equation here. And you see that because Fij is proportional to epsilon ijk bk, that we get this term here, and similarly the divergence, the time derivative of the electric minus the time derivative of the electric field is just this d0 f0 ij upper, and so that is equal to the current. So that's equations, that's the first two equations. The other set of Maxwell's equations come from these two expressions. So if we look at the first one, this is simply saying that the divergence of the magnetic field is 0. The second one here, this expression is the curl of the electric field. There's some error here. Oh no, that's fine. This is epsilon, not E. And this is the time derivative of the magnetic field. Are there any questions about that so far? Okay. So A and B, if you look at them, stare at them carefully enough, can be written into one Lorentz covariant expression, which is, which is this expression at the top. For instance, if we take, so this is 4 equations because there's one free Lorentz label, which is new on this, the way I've written it here. So if I take, for example, the nu equals 0 equation, then you see that we get J0 from the right-hand side has to be equal to the divergence of F mu 0, which is also the divergence of Fi 0, which is also the divergence of E. Equations, the C and D equations come from this equation here. Might as well put a box around this one. So again, this is has one free Lorentz label, which is mu. Epsilon mu nu rho sigma is the 4-dimensional version of the epsilon ijk. So we use a convention in which epsilon 0, 1, 2, 3 is 1, and totally antisymmetric, etc. So if I take mu equals 0 in that equation, I would get that this has to be 0, but then nu, rho, and sigma have to be purely spatial, which means epsilon 0 ijk, which is the same as epsilon ijk. And then from that, you get the divergence of B is 0. So an important exercise is to check the rest of these equations. Here I only did the time components of these 2 sets of equations. Please check that you get the rest of Maxwell's equations. Now, in electromagnetic theory, one introduces the scalar and vector potentials, phi and ai. And they're given by derivatives. With those, you can construct the electric and magnetic fields. So in some sense, phi and ai are more fundamental degrees of freedom because we derive E and B from them. And the equations for that are given here. So B is minus the curl of A. E is the time derivative of A minus the divergence of phi. Sorry, just minus the gradient of phi, sorry. And it's natural to combine these into a Lorentz 4-vector field, A mu. And if you then take these expressions, you see that they combine into a very nice covariant expression, which expresses the electromagnetic field strength in terms of a certain combination of derivatives of A mu. So A mu is called the electromagnetic gauge field for reasons that will become bit clearer in a moment. And A mu is the field which, if you quantize A mu, you get photons. So just write that. That's for something for you to learn later. So photons are the quanta of the electromagnetic gauge field A mu. Okay. So an exercise is, which is related to the previous exercise, given this formula for F mu nu, prove the C and D Maxwell's equations in a more sort of covariant way, let's say. Okay, now F mu nu and therefore Maxwell's equations, see, we've now, with this F mu nu, we've rewritten all of Maxwell's equations in terms of derivatives of F mu nu. What we're going to see is that this system has a huge symmetry, huge set of symmetries. So, and this symmetry is defined in the following way. Let's say that I was given A mu and I shifted it by the derivative of some function, any function essentially, or any function that has a derivative. With that shift, that allows me to define a new A mu prime. Well, let's compute F mu nu for this new gauge field. So d mu of A nu prime is just d mu of A nu, but now we get an additional term, which is d mu d nu of the function. So we're assuming that the function actually has is twice differentiable. And now let's compute F mu nu prime. Well, that's just given by the first line of this formula, but using the line above, I can do the calculation. So I'll get d mu A nu minus d nu A mu, which is my old field strength. Then I'll get a correction to d mu A nu, which is the one I just computed, and a correction to d nu A nu, which is the one I just computed. But you see that these last two terms are equal to each other, or equal and opposite to each other, because the derivatives commute with each other. So they contribute 0, and we see that F mu nu prime is F mu nu. Does anyone have any questions about this derivation? It's very important. So essentially, for any function that you can differentiate twice, that means an infinite dimensional space of functions. A mu prime and A mu give the same electromagnetic field strength, and therefore will describe equivalent physics. So I want to emphasize again that this is an infinite dimensional space of symmetries that Maxwell's equations have, because I could choose essentially any function here. So this transformation of the gauge field, just shifting it by a derivative of a function, is called a gauge transformation. It's called a gauge transformation because f is a function of space and time. So this is our first example of what are called local symmetries, because a mu shifts in different ways depending on x and t. And it's somewhat remarkable that these equations are gauge invariant. This is probably a good time for our break. So let's take 10 minutes. On my clock, it says 14:45. Pause the video. Get my charger. Okay, welcome back. So we were just saying that these type of transformations are called, these kind of symmetries are called local symmetries, as opposed to the symmetries that we've been studying up to now, like the Poincare transformations, which are global, meaning that the parameters are independent of the space and time coordinates. Now, this symmetry can sometimes be used, and is often used, to solve problems involving gauge fields by putting a mu into, let's say, calculationally convenient forms. And we'll probably see an example of that, if not later on, but then next time. Okay, so we now want to formulate the electromagnetic theory as a Lagrangian field theory. So since we're interested in Lorentz invariance, we need to find a Lorentz invariant Lagrangian that reproduces Maxwell's equations, which means we need to take F mu nu and build Lorentz invariance from it. And let's say at second, so, well, essentially there are only two basic Lorentz invariants that arise at second order, up to second order in derivatives. So if you recall, the Klein-Gordon equation was second order in derivatives. I could have added additional terms. I could have added, for example, d mu phi. I mean, I could have added, for example, the square of the kinetic term that we have to it, but we don't consider. I mean, we do. Those sorts of terms are important in general in physics, but at leading order, it's the terms up to two orders in derivatives which dominate the physics. So at second order in derivatives, we can have these two possible Lorentz invariant expressions, which I'm just calling 1 and 2. So 1 is just F mu nu lower times F mu nu upper, where we contract both the mu and nu indices. The other one, 2, is 2 F mu nu uppers, but with different indices, with the 4 indices contracted by the epsilon tensor. So an exercise for you is to calculate both of these as an explicit expression in terms of E and B. So let's consider the first type of term. So we'll consider a Lagrangian based on that type of term, where A is some constant, some constant. Eventually we'll see that A actually has to be negative, and in fact fixed to be equal to -1/4 in Heaviside units. So in other words, A equals -1/4 is going to get fixed by requiring that we reproduce exactly the Maxwell's equations as we've written them down earlier. So now this expression, F mu nu has 6 non-zero entries. So F mu nu, this, this Lagrangian f mu nu squared, as it's sometimes called, has a bunch of terms involving different combinations of derivatives of the gauge field. So, so we want to work out the Euler-Lagrange equations for this action, and in order to do that, we need to understand the expression f mu nu squared a bit better in order to do the calculation precisely. Okay, so f mu nu is d mu a nu minus d nu a mu. So the action depends on d mu a nu, but not on a mu. So in the Euler-Lagrange, the general Euler-Lagrange equations, which we've got somewhere back here, okay, there we go. The left-hand side is not going to contribute because there's no, because dl by dA mu is 0, because the Lagrangian doesn't depend explicitly on a mu, only on the derivatives. But the second term will contribute. Okay, now, so as I was saying, we have to do this computation carefully to get the coefficients of the various terms correctly. So the next few minutes, we're just going to walk through this calculation. So let's consider this expression A, which is like what we have in our proposed action, except this expression has two uncontracted indices. So we've only contracted the mu index, but we have a free nu index and a nu prime index. So the reason I've written this one down is because we want to, in order to calculate f mu nu squared, we have to do it in 2 steps. So let's look at the first line in equation A. So we just have f0 nu lower times f0 nu prime upper plus the spatial terms fi nu lower fi nu prime upper. Good. So in order to then go from, I'm not sure why I've written this expression twice, but some reason I did. Oh no, I did, sorry, the expression below. The expression below is just to indicate that we'll have to just eventually sum over the spatial components. This is not actually an equation. I'm going to remove that because it might cause confusion. So we can go from equation A to the quantity of interest now. By now we just sum over nu and nu prime. So we set nu prime equal to nu, and then this term, sorry, the first term in expression A will give us this term, and that's all. Whereas the second term in expression A gives us a term when nu is equal to I, and a term in which nu is equal to j. So the end result is that f mu nu squared is twice f0i lower times f0i upper plus fij contracted with fij upper. Now, so we'll keep that expression in mind, the one at the bottom. And now, now we'll look at the Euler-Lagrange equations. So we've got 4 fields, A0, A1, A2, A3. So we'll have 4 Euler-Lagrange equations. And I've written them explicitly at the bottom. And obviously the left-hand side is 0 for the action that we're studying at the moment. So we've got these different contributions at the bottom of the slide here, and we need to look at these 2 different contributions and do the variation of the Lagrangian for those 2 types of term. So the first type of term is so F0i is D0ai minus DIA0, but F0i upper has a minus sign. So that's why we have this minus sign here. And if I just literally expand out the 4 terms, you see that we get one term which is minus D0ai all squared, coming from this times this. We get D0ai times DIA0. Here, remember, we're summing over I in the end. So this term comes from this times this, and we get this term here from this times this, and then the last term is DIA0 squared. Okay, so we write that like that, as I've written here, and now I want to consider the variation of F0i squared with respect to dJ Okay, so what do we get from that? Well, here you see that we'll get, I'll set I equals to J and it's squared, so I get a 2 and a minus sign, and the coefficient is dJ0 itself. But there's another contribution from here, which is 2 times D0aj, this should be, sorry, typo. And this expression, you see, D0aj minus dJ0 is actually F0j. Does anyone have a question about this derivation? Hopefully I've done it slowly enough. But it's important, anyway, it's important to be able to do this derivation. Similarly, we also have to compute the derivative of the functional with respect to D0ai. Let me call this J, sorry. Oops. It should be J's because I'm using I in the summation convention of the action. So if I differentiate respect to D0aj, I'll get a minus 2 times D0aj from that term, and I'll get a plus 2 dJ0 from that term there. And these combine to give me twice Fj0. So it's nice that when you vary this Lagrangian with respect to the derivatives of the fields, the answer you get is gauge invariant, in the sense that the answer is given in terms of the field strength, or at least part of the field strength so far. Okay, we also need the other terms, which is Fij squared, remember. So we just looked at the first term at the bottom. We now want to look at the second term. Well, let's work that out carefully as well. And we'll do that by just first summing over I and not over j. Well, if I do that, I'll get 3 terms. F1j lower, F1j prime upper, plus the corresponding 2 terms for when I is equal to 2 and 3. And so each of these is going to be 2 terms, because I've got, so this one gives me F12 squared plus F13 squared. Similarly, you know, this one's going to give me F21 squared plus F23 squared. So we'll get 6 terms in total. And those 6 terms are actually 2 copies of 3 terms, which are F12 squared, F13 squared, and F23 squared. So you can check that if I now, for example, take the derivative of Fij squared, sorry, with respect to d1 of a2, for example, that I get 4 times F12 in return for that. So that's very similar to what we had on the previous slide, but I've skipped the lines. And in general, the key formula, is this one. So now I can combine everything that I've done into one Lorentz covariant formula. So the point is that the derivative of f mu nu squared with respect to d rho a sigma is 4 times f rho sigma upper. So that's something that you can now prove. So therefore, if the Euler-Lagrange equations are given by a times f mu nu squared, sorry, if the Euler-Lagrange equations are derived from a times the integral of f mu nu squared, we will get that 4a times the divergence of f rho sigma is 0. And if you recall, that half of our Maxwell's equations, the A and B, are given in terms of the divergence of F. So that's nice that we get something proportional to the divergence of F. Now, in the absence of a current, or in the absence of any source, J mu would be 0, and this action, F mu nu squared, would give you the vacuum Maxwell's, well, half of the vacuum Maxwell's equations. But in the presence of a current, we need to modify this f mu nu squared in order to include sources and interactions. So the way we do that is by adding to the Lagrangian a nu j nu, and then that term which was 0 on the left-hand side before becomes equal to j nu. And with that modification, we need to put a equals to -1/4 in order to reproduce Maxwell's equations in Heaviside units. If I'd have added minus a nu j nu, then we would have said a is +1/4, but actually that's not possible. And it's not possible for the following reason, is that a has to actually be negative. If you expand out f mu nu squared, you get a term which is minus the time derivative squared of a, of the spatial components of a. So if a were positive, if you considered a situation in which the vector potential was rapidly varying in time, this term would cause S to be negative and unbounded if A were bigger than 0. So we actually need A to be negative. So it's important to check that when you're working with Lagrangians, that the quadratic terms in the time derivatives of the fields are positive in order to have a well-defined field theory. We would have opposite signs, just to let you know, if we were using mostly plus convention for the Minkowski metric. Okay, that was f mu nu squared. What about this other Lorentz invariant quantity, epsilon f times f? Well, this quantity turns out to be a total divergence. So I'm going to leave that as an exercise. It's a nice exercise, useful exercise for you to show that this other term is a total divergence. So being a total divergence, it's not going to contribute to the equations of motion. Okay. So are there any questions about this formulation of Maxwell's theory before we move on?
Professor, I didn't quite understand why is the reason that S cannot be negative and unbounded?
Because this is the kinetic energy of the field, which you don't really want that to be negative. Is another way of putting it.
Right. Yeah.
Any other questions? All right, we'll just say a few more words before we close. Let's look at Maxwell's equations in a bit more detail. So d mu of f mu nu is actually d mu of d mu a nu minus d nu a mu, of course. So that gives us two terms one of which is looking familiar. So this is just d mu contracted with d mu acting on a mu, which is part of which would be the Klein-Gordon operator, if you like, for zero mass. But then we have a second term which spoils that interpretation. However, d mu times, I mean, this divergence of the gauge field is just a single function. And since the gauge symmetry also depends on a single function, we could simply choose that function to be such that this is equal to 0. So this means we're choosing a gauge, but we're free to choose the gauge because the equations have that symmetry, but we have to remember that we've chosen a gauge. So if we do choose that gauge, then Maxwell's equations become these equations here, which is simply, you can write it as, for every index nu, you've got a Klein-Gordon equation with some source term on the right-hand side. So in the absence of sources, so if J mu is 0, then the free particle solutions are the same as the solutions of the Klein-Gordon equation, namely just these e to the I p mu x mu solutions. But the coefficients can be different for each value of mu. Obviously, p mu has to be, for the Klein-Gordon equation, we had p mu squared is equal to m squared. Well, now it's equal to 0 because the photon has a 0 mass, which, by the way, comes out automatically from this Lagrangian. So, so that's actually a prediction of this theory. And really, that's a consequence of the gauge symmetry. Because the gauge symmetry forces f mu nu to take that particular form. And it's because of that form that the photon is massless. Now, the coefficient of each of these terms is in fact where the polarization of the photon is taken into account. So as a classical plane wave solution, you can take into account the different polarizations by choosing appropriate values for the components of epsilon mu. For the particle solutions, only solutions annihilated by p mu would be acceptable. Because when we wrote, now this is where the gauge choice comes back. That means P mu, A mu is actually 0. Which is the same as P mu epsilon mu equals 0 for these solutions. And this leads to two independent polarizations. Okay, so which correspond to the two helicity states, as to make contact with the representation theory we did of the Poincare group. So I think that's probably enough for today. I'll stop the recording and we can take if anyone has any questions.
Sure. So when we consider the term of Lagrangian that has the form of epsilon mu nu rho sigma and f mu nu f rho sigma.
Yeah.
And your exercises were write it as the total derivative of a current. So I guess that this current must be like Gauge invariant in order to it must be vanish at infinity, right? So it must be Gauge invariant.
It is gauge invariant. As you will see when you do the exercise.
Yeah, okay.
Professor, I wanted to ask if there's any book you would recommend for this part of the course?
Yeah, actually this part, well, the Maxwell part is Landau and Lifshitz. I think I'm more or less following, I think I'm even, I have exactly the same conventions as them. So most of what I talked about for the Maxwell equations is in the Landau-Lifshitz chapter. I don't know, anyway, you'll find it. There's a chapter on electromagnetic fields. There they cover a lot more also, the physics of electromagnetism, which I'm not going to talk about, but the equations are all there. So I guess that's the last exercise. So let's I can't remember what. So actually, so these lecture notes I kind of added on to week 3. Where did we stop the exercises last time? Last week. Can someone remember?
I think page 21.
21. Oh, so we didn't have these ones.
Yeah, I think so.
So it's 21.
It was 28, I guess.
Yeah, 28 rings a bell.
Yeah, I think so too.
Oh yeah.
Okay. 28. So okay, now let's see how much we've got. We've got a few exercises on particle decays. Conservation law. Yeah, I think we can go all the way to the end of today then, which is page 89. I'll send this afterwards. In the file, so I've been preparing Thursday's lecture as well, which I still have to go through to check. So feel free to read ahead, but it's not complete yet. So we'll go up to page 89. Yeah, so there'll be the usual tutorial tomorrow. And I think I can't think of anything else I need to say. Does anyone have any other questions, even practical questions, if there are any?
Professor, again about the book, for the previous part when we were talking about the Klein-Gordon equation and the Poincaré group, I don't think that's in Landau, right?
No, it's not. I will get you another reference for that.
Okay.
But you'll see that you know, we're in the next lecture we're going to actually go through the Noether currents for the Poincaré group and all the formulae. And yeah, but I'll try and dig out another reference on that.
Okay, thank you.
All right, everyone. So have fun in the tutorial tomorrow, and see you on Thursday then in class.
Thank you, Professor.
Thank you.